Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate combinatorics based on my book, Invitation to Combinatorics. This particular lecture is about generating function, and we're going to use generating functions to count combinations of multisets. And it's based on section 9.2 of my book. So let's get started. We start with a guiding problem, a problem that we sort of tell us what kind of a problem we want to solve. So let's say that you want to make a basket made up of 47 pieces of fruit. You're going to have apples, bananas, oranges, pears, and peaches. And the number of apples is going to be even and at least 2. So 0 is not allowed. You have to have at least 2 apples. The number of bananas has to be a multiple of 5. The number of oranges can be anything you like. The number of pears is between 0 and 4. So it can be 0, 1, 2, 3, or 4. And the number of peaches has to be 0 or 1. So these are sort of random sounding kind of conditions. So we want to make these baskets of fruits. And what's our question? The question is that in how many ways can you make such a basket? This is the kind of problem that we want to try to solve. So first, let's look at different ways of looking at this problem, equivalent formulations for this. This is the same as saying that you have 47 identical balls. That means that you want to pick 47 things, but you want to put them in 5 distinct boxes with unusual capacity restrictions. So one box only takes even number, and that even number has to be at least 2. Another one is only between 0 and 4. Another one, the one labeled bananas, is only multiples of 5, and so forth. So for each one of the fruits, we have a box. And if we put a ball in that box, that means that we are picking one of those fruit. But those boxes, the one for bananas, the one for apples, for pears, for peaches, each one of them has certain kinds of capacity restriction. Again, one of them only takes multiple of 5 balls. One of them only takes even number of positive even number of balls. Another one can be anything, but one of them can only be between this number and that number, and another one can only be 0 or 1 ball. Another way of thinking about that is that you want the number of non-negative integer solutions to x1 plus x2 plus x3 plus x4 plus x5 equals 47. Again, with x1 being even, x1 is going to be the number of apples you pick, even and at least 2. x2, the number of bananas, is a multiple of 5. x4 is between 0 and 4. x3 is just a non-negative integer solution, and x5 is between 0 and 1. Okay, so again, you can think of these are models that we have used before for counting problems. You can think of balls in boxes or non-negative integer solutions for certain kinds of combinations, and this is an example. The way we have described it is we want to count combinations of multisets. We have a multiset with infinite repetition numbers, you might think, and with 5 types, and we want to pick a combination, but with restrictions, and the restrictions were specified in the problem. What we will use today is to use ordinary generating functions for solving this problem. And so the first thing we want to do is I want to do a proof of concept. I want to prove something, show you something simpler and show you how basically this is done. And in fact, if you understand this slide, you might be able to skip the rest of the talk. But the rest of the talk will go in a lot more detail. So, and at the end, for example, I'll give you applications to partition functions. So let's say that I want to find the number of integer solutions to x1 plus x2 plus x3 equals 47, where x1 is a multiple of 7, x2 is between 0 and 6, and x3 is it can be any non-negative integer. So it's a simpler than that because there's not 5 things, there's only 3 things, but there are that kind of a restriction as we had before. And the question is, what does generating functions have anything to do with this? How can calculus kind of techniques help us with a discrete problem, a counting problem such as this one? And so the point is that consider the following product of infinite power series. So look at 1 plus x to the 7 plus x to the 14 plus ... forever times 1 plus x dots plus x to the 6. This is actually a polynomial. And then 1 plus x squared plus 3 dots. Now, I'm going to explain what this has to do with the problem we want to do. So And the way we are going to do that is by asking the following question. If you multiply this out, what is going to be the x to the 47 term? Will there be an x47 term? And if so, what will be the coefficient? And when do you get an x to the 47 term? Well, you will, whenever you're multiplying this out, you will have to take one term from the first parentheses, one term from the second parentheses, one term from the third parentheses, and multiply them. And for example, you might get x to the 47 if you pick x to the 7th plus the first one, x to the 6th from the second one, and x to the 34th from the last one, because the exponents add up to 47. This gives you an x47 term, but it's not the only way. For example, you could also pick x to the 28th from the first one, x to the 3rd from the second one, and x to the 16th in the third one. So anytime that I pick three terms, one from each one of these parentheses, and their exponents add up to 47, I get an x to the 47 term. So now the exponents, though, if you look at them, are actually the solutions to that equation x1 plus x2 plus x3 equals 47 that we were seeking. Why? Because the first exponent, since it's coming from the first parentheses, it's always going to be a multiple of 7. The second one is going to be between 0 and 6. And the third one could be anything. And so when I find one of these terms that gives me x to the 47, if I look at the exponents, I really have a solution to x1 plus x2 plus x3 equals x47, satisfying the weird conditions that I had put. So the question is, how many of these solutions are there? And that's the same as saying, how many x to the 47s I get? So to answer that, all I have to do is look at the coefficient of x to the 47. So the number of such terms is the number of solutions, and that's the coefficient of x to the 47 in the product. Because every time you get an x47, you're adding an x47 to the group of x47s. And so if you get 131 of them, then that means that there was 131 solutions. If you got 1,000 of them, then that means that the number of solutions was 1,000. So that was our proof of concept, in the sense that if I know how to deal with these kinds of power series, and if I can glean from that what the coefficient of x to the 47 is, I have the solution to my question, which is the equation x1 plus x2 plus x3 equals 47 has how many solutions, where the solutions are integers. The first one, x1, is a multiple of 7. The second one, x2, is between 0 and 6. And the third one can be any non-negative integer that you like. That's going to be the coefficient of x to the 47 when you multiply this out. And in fact, in the previous lectures, we have dealt with power series like that, and we can put them in a closed form, and we can try to glean from that what the coefficient of x to the 47 is. It's not always easy, but sometimes possible. Okay, I could do that now and continue with this line of discussion, but I want to make it a little bit more formal to have a little bit more vocabulary so that I can talk about these things a little bit easier. And so for that, I first will want to introduce this thing called the indicator power series. It sounds like a fancy name. We like fancy names. That makes us look smart, but it's actually a pretty straightforward concept. So let's say that you have a set of non-negative integers, n1, n2, so on. This could be multiples of 7, numbers between 0 and 6. It could be all non-negative integers. It could be anything you like, any collection. It could be multiples of 5 and so forth. Then you are going to define a power series. These are actually the power series I used in that proof of concept problem. That's going to be x to the n1 plus x to the n2 plus x to the n3 and so forth. So you take the numbers you have in your set and you just make them the exponents and then add them. Pretty straightforward. This chi of t, I'm going to call the ordinary indicator power series of t. It's indicator because if you have this, just look at the exponents and you know what your set is. So instead of saying this is the set of non-negative integers I like, I can write down this power series and the exponents tell me what's in that set. Nothing too complicated. Let's just go through some examples and see that we actually have the tools to write these things sometimes as in closed form. So if you look at positive even integers, then the indicator power series, well, it's x squared plus x to the 4th plus x to the 6th plus 3 dots. all the positive even ones. But what's the closed form for that? Well, we start with our favorite, which is 1 over 1 minus x. We know that that's the sum of the geometric series, 1 plus x squared plus ... If you don't know that, watch my earlier videos. And so if I want powers, even powers, instead of x, I plug in x squared. Wherever I see x in here, I put x squared, and I get 1 over 1 minus x squared on the left-hand side, but on the right-hand side, I get 1 plus x squared plus x to the fourth, and so forth. This is almost what I want. It has an extra 1, so I could subtract that 1, or I could multiply both sides by x squared. Either way, I get that the closed form for that indicator power series. So x squared over 1 minus x squared is the same as 1 over 1 minus x squared minus 1. If you combine terms in this one, in the right-hand side one, you'll get the other one. But anyway, either one of these is a closed form for the indicator power series for the positive even integers. What about if you have a finite set, numbers between 0 and 10? Well, the indicator power series is going to be just a polynomial, 1 plus x squared all the way to the x to the 10th. And what's the closed form of that? Well, this is a partial sum of a geometric series, and you probably know what that is also. I never remember, but I remember how to find it always. You multiply by the common ratio, in this case x times chi of t, and when you do that, everything gets shifted. You get x plus x squared plus x cubed all the way to x to the 11th. Why did I do that? Well, I did that because if you now subtract these two things, chi of t minus x chi of t, most things cancel. From chi of t, the only thing that doesn't cancel is 1. The only thing that doesn't cancel from x times chi of t is x to the 11th. So I have 1 minus x to the 11th. I can factor chi of t on the left, divide by 1 minus x, and I get a closed form for this indicator power series. But this is, again, another review of the partial sum of a geometric series. Okay, now that we talked about indicator power series, the key is how do we multiply them? What happens when you multiply them? And that's really the thing that we're interested in. So let's say that we have a whole bunch of them. So this is also a review of multiplying power series as we had seen in a previous lecture video that was devoted to that. So what happens when you multiply power series? We're going to apply that to indicator power series, but first we want to just see what the general situation is. So let's say that F1 is the ordinary power series. OPS stands for ordinary power series, the ordinary generating function for this sequence of numbers. They have all superscript 1, and then it's A0, A1, A2, and so on to infinity. I had the superscript 1 because I want the second one to have superscript 2, and so on. I have T of these T functions that are the ordinary power series, the ordinary generating function, each for a different sequence. All those sequences, and going from 0 to infinity, they're distinguished by their superscripts. Then if you have that, and if you multiply them, of course, when you multiply these functions, you get a new function. That function is also the Taylor series at x equals 0, or the power series for another sequence of numbers. The question is, what that is? And we have seen in previous lecture that what that is that to get that, you have to multiply one term from each one of those original sequences, and then the coefficient of x to the n, which is what Cn is going to be, you multiply the ones where their subscripts add up to n. So whenever these subscripts add up to n, you get another term that you have to add up to get Cn. And in general, this is complicated to find. But sometimes, for example, when all of them are 1, which is the case in our indicator power series, they're all either 1 or 0, this will become a lot easier to find. So if T is a positive integer and S a non-negative integer, so this is the theorem that's going to, the main theorem that's going to formalize the thing that we saw in that one example. And let's say you have Ni, which is a set of non-negative integers. You don't have just one of them. You have N1, N2, N3, N4, all the way till Nt. Each one of them is a different set of integers. One of them, for example, could be multiples of 5, which is, for example, what's allowed in terms of the number of bananas. Or another one could be even integers, but positive, and that would be the number of apples that are allowed. So we have T of these sets of non-negative integers. Each one of us each one of them telling us the conditions on one of the guys that we want. And we're interested in the number of solutions to x1 plus x2 plus x2, 3 all the way till xt equals s, when each xi, x1 is n1, x2 is in n2, x3 is in n3, and xt is nt. So we have picked these sets that tell us what the restrictions are for each one of our variables, and we want to know what the number of solutions is, and we have called the number of solutions CS. That's exactly the problems that we started out with, or the second problem. Both of them are of this form. And we now want to find its ordinary power series. And the question is that what's the ordinary power series, the ordinary generating function for this sequence of numbers? The number of solutions to x1 plus 3 dots plus xt equals s. So s, when s changes, the number of solution changes, and that gives us the sequence. And the answer is that, well, what you need to do is you need to find the indicator power series for each of these guys, for n1, for n2, for all the way till nt, and then you multiply them. And when you multiply them, you will get the power series for the number of solutions that you want. And that's what we saw. We took the indicator power series, those three things that I showed you in the proof of concept slide, were indicator power series, and you multiply them, and you would get the generating function for the number of solutions that you want. Okay, why is the proof? What's the proof of that? Well, so again, each ni is a set of non-negative integers. This is for I between 1 and t, and chi of ni is that. That's well, you might say the indicator power series didn't look like that, but I'm going to write it in a slightly different way that I did before for my purposes. So I'm going to put the coefficients as a01 I, a1 I x, a2 1 a2 I x2, all the and so on. And so my typical term is going to be an superscript I xn plus 3 dots. But is that really an indicator power series? Well, not quite, but it is if I tell you what these coefficients are. The coefficients are either 1 or 0. They're 1 if that subscript k is in ni, and 0 if it's not. So if you plug these in, you will get the same indicator power series that we had before. We have a bunch of 1s and 0s. Zeros just go away. The ones that are 1, then the exponents are exactly the terms in our sequence. And so this is exactly the same indicator power series as before. And now, when I multiply them, then what do I get? Well, I will get the ordinary power series of something, ds. But what's ds? And ds, by the theorem in general that we said, is that, well, you've got to multiply one of these coefficients from each one of those indicator power series, but you've got to make sure that these coefficients add up to s. But these numbers are either 1 or 0. If any of them is 0, then the whole thing is 0. So for us to get any contribution from this, all of them have to be 1. And how is all of them have to be R1? All of them are 1 if x1 is in n1, x2 is in n2, x3 is in n3, and so forth. So instead of having x1 plus x2 plus 3 dots plus xt equals s, we have that they are still equal to s, but they also have to be in their corresponding subsets. So and then at that point we get 1. So we get x1 plus x2 plus xt equals s, but we also get that xi has to be in ni, because if xi is not in ni, then the corresponding term in that sequence would be 0, and we would not get a term. The only time we get a 1 is if all of them satisfy that question, that's condition. And so when you're adding 1s, so the only answer is going to be the number of solutions, and the number of solutions was CS, and that's what we wanted to prove, that CS is that this function that we got by multiplying these indicator functions is the ordinary generating function for CS. And we saw that the coefficient of x to the s is CS. So that proves that. So this is really, also, I just wanted to show you that we have been organizing our counting problems in terms of this counting table. So we have S balls and T boxes, and we're going to put all the balls into the T boxes. The ith box going to contain UI balls. and there's going to be some conditions on those. And the problem that we just solved is this entry 16, where the boxes are distinct. We have different boxes, one for bananas, one for pears, one for apples, but the balls are identical. So we're just choosing them. We're not ordering them or anything. We're just choosing which ones. But the conditions on how many balls are in each box are depend on these NIs, these subsets that are going to be different. So so this problem that we just solved is dealing with this box 16 in our counting table. And by the way, this is the more general of everything in this column. If you can do this, you can use actually the same method for all the other ones. It's just that we had much easier methods for doing 2, 6, and 10, and 14 we did with inclusion-exclusion principle. But we can also do it with generating functions. So now let me bring together all the various interpretations that we have. That if we have a set of integers n1, n2, and 3 t sets of integers, non-negative integers that are going to give us restrictions on what we want, and if we take their indicator power series, we also are going to have a multiset with t types and infinite repetition numbers, then the following integers are all going to be equal to each other. And this is something that we have discussed before, but we are now just going to add one more item to this set. One is that the number of solutions to x1 plus x2 plus all the way till xt equals s. As long as each xi can't just be anything, it has to be an element of ni. So x1 has to be an n1, x2 has to be an n2, and so forth. So that number is the same as all the other ones. The next one is that you take s combinations of m, where the number of ui picked is an element of m of ni. Again, you want to pick s things out of this set, this multiset m, but you have restrictions. How many u1s you can take has to be something in n1. The number of u2s has to be in n2. And of course, that's the same as the first formulation, because x1 is going to tell you how many u1s to pick. x2 is going to tell you how many u2s to pick. Or if you've already picked u1s and u2s, then that tells you the solution to this equation. And the third thing is the entry 16 in our counting table, which we just talked about, is the number of ways of placing s identical balls in t distinct boxes, such that the number of balls in the ith box is an element of that set ni. So in the first box, we get a number that's in n1, the second box, a number that's in n2, and so forth. And finally, the new thing, the new kid on the block, is that this is also the coefficient of x to the s. We wanted x1 an s combination, x to the s in the function chi n1 times chi n2 times chi nt. So the product of those indicator functions. Okay, so that's the theorem we have, but now let's just look at some examples. But before we do that, let's remind you some important power series that we're going to use along the way. One of the ones, maybe the most useful one is 1 over 1 minus x to the t. That is the power series for multi-choose numbers, t multi-choose 0 plus t multi-choose 1x, and so forth. A typical term is t multi-choose n times xn. And we prove this by also multiplying the power series for 1 over 1 minus x with itself t times, or you can do that by induction if you like. A special case of this is 1 over 1 minus x, which is the closed form for the geometric series, and we can get things from that by, for example, plugging in x to the fifth for x. If wherever we have x, we put x to the fifth, we get the closed form for 1 plus x to the fifth plus x to the 10th plus x to the 5th and so on forth. Another one to know is partial sums, which talked about this. Again, partial sums of geometric series are of the form 1 plus x to the 10 is going to be 1 minus x to the 11 over 1 minus x. And finally, one that we actually will not use today, but it's a useful one to know, is the binomial theorem. 1 plus x to the n is the closed form for the binomial coefficients, one row of the Carré-Giglia triangle, also known as Pascal's triangle. Okay, so now let's go back to our guiding problem. Again, let's remind you, we want to have baskets of 47, either apples, bananas, oranges, pears, and peaches. the number of apples has to be even, at least 2, bananas at a multiple of 5, oranges can be anything, the number of pears between 0 and 4, and the number of peaches is going to be 0 or 1. And how many ways can we do that? And the insight is to replace 47 with n and call the solution Hn. So Hn is the number of baskets of n fruit that we can make, but with the same conditions. And so then we want to find the generating function for this infinite sequence. And this is the product of indicator generating functions by our theorem, because we are finding a sub-multiset of a multiset with 5 types of elements and with infinite repetition numbers. Okay, so we have to find the indicator power series for each fruit. And for the apples, we have x squared over 1 minus x squared. For bananas, we have 1 plus x to the 5th plus x to the 10th, because they were supposed to be multiples of 5. For apples is x squared plus x to the 4th plus 3 dots. Why is that x squared over 1 minus x squared? Because if you start with 1 over 1 minus x, that's 1 plus x squared plus x cubed and so forth. If instead of x you put x squared, you get 1 plus x squared plus x to the 4th, so forth, equals 1 over 1 minus x squared. Then if you multiply it by x squared, you get rid of that 1 and it becomes x squared plus x to the 4th plus 3 dots. 1 plus x to the 5th plus x to the 10th is just replacing x by x to the 5th in the geometric series. And so we get 1 over 1 minus x to the 5th. For oranges, we can have anything we like. So it's just 1 plus x squared, whatever. And that's just the geometric series, 1 over 1 minus x. For pears, we have 1 plus x plus 3 dots plus x to the 4th, because it was between 0 and 4 inclusive. And that's a partial sum of a geometric series. Is 1 minus x to the 5th over 1 minus x. For peaches, it's 1 plus x. And if we multiply these, so we have got 5 of them, chi n 1 times chi n 2 times that chi n 5. In the title here, I have that typo. That should be chi n 5. So if you multiply these, actually, this problem is made up in the sense that life is going to be easy here, because a lot of things cancel. 1 minus x to the 5th cancel, 1 plus x cancel, 1 minus x squared, because 1 minus x squared is 1 minus x times 1 plus x. So we're left with x squared over 1 minus x cubed. That's going to be the generating function for the number of fruit that we can put in a basket if we want n fruit. Okay. Now, so this is the ordinary power series of the sequence we want. We generalized the problem. We made it harder by not focusing on 47 fruit, but saying n fruit. So the number Hn is going to be the coefficient of x to the n. H47 is going to be the coefficient of x to the 47. But how are we going to find that? Well, how we're going to find Hn? We now work backwards. We say, well, 1 over 1 minus x cubed. What is that? Well, that is the ordinary power series of multi-choose numbers 3 multi-choose n. Okay? But what happens when you multiply by x squared? When you multiply by x squared, x to the n becomes x to the n plus 2. So what's the coefficient of x to the n? Well, x to the n minus 2 becomes x to the n after you multiply it by x squared. And the coefficient of x to the n minus 2 was 3 multi-choose n minus 2. So that will become the coefficient of x to the n. This will become the coefficient of x to the n. And therefore, x squared over 1 minus x quantity cubed is the ordinary power series of that. And so Hn is 3 multi-choose n minus 2, or n choose n minus 2, or n choose 2, or n times n minus 1 over 2. And in particular, H47 is 1,081. So there's 1,081 baskets of fruit we can make with those conditions. Let's do our proof of concept theorem also, problem also. So how many integer solutions to x1 plus x2 plus x3 equals 47? If x1 is a multiple of 7, x2 is between 0 and 6, and x3 can be anything that we like. So Hn is going to be the number of solutions to x1 plus x2 plus x3 equals n with the same restrictions. And then we find the indicator power series for multiples of 7 is 1 plus x to the 7th plus x to the 14th. And that's the same as the geometric series with a common ratio of x to the 7th. And so it's 1 over 1 minus x to the 7th. For x2, we only have numbers between 0 and 6 as possibilities. So the indicator power series is actually a polynomial, is a partial sum of a geometric series, and that's 1 minus x to the 7th over 1 minus x. And the last one can be anything, so it's just 1 over 1 minus x, the geometric series. Then we have to multiply these, and when we multiply these three, we again, this has been doctored so that nasty things go away, and we get 1 over 1 minus x squared. And we know that that's the ordinary power series of multi-choose numbers, again, 2 multi-choose n. And so H47 is going to be 2 multi-choose 47, which is 48. Choose 47 is 48. Actually, since the answer is so easy, you might suspect that there's an easier way of doing this problem, and there is. If you look at the conditions here, x3 can be anything between 0 and 47, and that's 48 choices. So you pick your x3, and then after that, like for example, you might pick x3 to be 20. Then you have 27 things for x1 plus x2. If you take 27 and divide it by 7, you'll have a quotient and a remainder. The remainder is going to be between 0 and 6, and that's going to be x2. The quotient is going to be the answer to x1. And there's always one quotient and one remainder, as long as you make the remainder between 0 and 6. And so for every choice of x3, you have exactly one choice for x1 and x2. And so the number of solutions is 48. But that's not something that you would have thought of to think of that way, unless you saw the answer and say, why is there only 48 solutions? Finally, I want to now turn to ask you, well, I mean, these problems seem very contrived. Like, why would you want the number of bananas to be a multiple of 5? And so I want to show you that actually these kinds of conditions do come up in something that we have seen before. So we're going to apply what we just saw to partition numbers. So and we'll come back to this in a future lecture and talk about this in more detail. But let's say, recall that P of n counts the number of partitions of the integer n. So that means a bunch of positive numbers that add up to n, and the order of those numbers does not matter. So 2 plus 1 is the same as 5 plus 2. Now, P of 4, for example, how many ways can you write 4 as the sum of other integers, positive integers? And it's 5, because the only ways you can do that is if you have 1 plus 1 plus 1 plus 1, or 2 plus 1 plus 1, or 2 plus 2, or 3 plus 1, or 4. And there's 5 of those. So those are all the partitions of 4, and there's 5 of them. And so P of 4 is 5. But now what's P of 11? Well, I mean, the way we have dealt with this previously is that you look at partitions of 11 into one part, into 2 parts, 3 parts, 4 parts, 11 parts, and then add them. And for each of, and how do you find those? Well, for those we have recurrence relation, which means that you first find partitions of 10 and 9 and 8 and so forth, and then you make your way down to finding partitions of 11. But generating functions provides another method, a very powerful method for gleaning information about partition numbers. Okay, so let's reformulate this idea of finding numbers that add up to 11. So we might want a bunch of 1s, a bunch of 2s, a bunch of 3s, a bunch of 4s, a bunch of 11s that add up to 11. That's what finding a partition means. Now, of course, if you use any 11, then you can only use 1 and you can't use anything else. You can never use 12, 13. That's why we don't have them. But a priori, you can reserve judgment. We can say that we want to find A11s, A22s, A33s, and A1111s to add up to 11. And I want to know what are the choices possible for A1, A2, A3, and 11. And the number of those choices is the partition number 11. So reformulating that one more time, P11 is really the number of non-negative integer solutions to A1 plus 2A2 plus 3A3 plus 11A1 equals 11. And I can even change that around. I can say that P11 is the number of non-negative integer solutions to B1 plus B2 plus B3 plus B11 equals 11. So instead of B1, A1, I put B1. Instead of 2A2, I put B2. Instead of 3A3, I put B3. Instead of 11A1, I put B11. So these are not going to be exactly the same. They will be the same if I make the extra condition that B2 is a multiple of 2, B3 is a multiple of 3, B11 is multiple of 11. So now we come to the kind of conditions that we had seen previously. So as long as you make the condition that Bi is a multiple of I, and you want the number of non-negative integer solutions to be 1 plus B2 plus 3 dots B11 equals 11, you are finding P11, the number of partitions of the integer 11. And now we know how to do that. We just have to multiply a bunch of indicator power series. So I'm repeating what I just said, that P11 is the number of non-negative integer solutions to B1 plus B2 all the way to B11 equals 11, where Bi is a multiple of I. And then for each of these, the indicator power series are going to be x to the 1 plus x to the I plus x to the 2i. Those are multiples of I. And they're just a geometric series with a common ratio x to the I. So it's 1 over 1 minus x to the I. You can think of it that way, or you can think of it as starting with 1 plus x squared and replacing every x with xi. So that's that. So what we're going to do is P11 is the coefficient of multiplying all of those indicator functions. So I have to multiply 1 minus x with 1 over 1 minus x squared, 1 minus x, all the way to the 1 over 1 minus x11. Why do I need that much? Because 1 over 1 minus x3 tells me how many 3s I'm going to use in my partition. 1 over 1 minus x to the 7th tells me how many 7ths I'm going to use. And the coefficient of x to the 11th is going to be the total number of partitions. Now, this is not that easy to do by hand. It's not like the problems we saw where things cancel and we can just say, oh, we know what power series this is. This is not that easy to solve. But it's now a calculus problem. So the question is that what's the coefficient of x to the 11th in the Taylor series at x equals 0 for this function? And you can use a symbolic algebra system like Mathematica or Maple or Sage to answer that question. So in Maple, I used Maple, Taylor and I found the Taylor polynomial of degree 11 for f of x, and it's this thing. And so that 56 is P of 11. 56, which is the coefficient of x to the 11, is the number of partitions of 11. And in fact, if you think about it, the number of partitions of 10 is going to be 42, because including that 1 over 1 minus x to the 11th is going to have no effect on the coefficient of x to the 10th, because this thing, when you expand it, is 1 plus x to the 11th plus x to the 22 plus x to the 33 and so forth. So when you multiply it out, it doesn't affect the coefficient of, if you put it in or not put it in, the coefficient of x to the 10 in the result is going to be the same. So this Taylor polynomial is telling me all the partition numbers up to 11. So 1, 1, 2, 3, 5, 7, 11, 15, 22, 30, 42, and 56 are all the partition numbers up to 11. And you have to admit that it's quite surprising that somehow or another calculus, finding Taylor polynomials, has anything to do with finding partition numbers. How many ways can you partition an integer? And we were able to use a powerful system like Mathematica or Maple or Sage that do symbolic algebra for us to be able to answer this question. This is the end of this lecture. Till next time, well, we also see applications of generating functions, but to solving recurrence relations. Till next time.